Distributed systems top interview questions. Step-by-step introduction. Distributed systems are systems where multiple computers work together as one larger system. Software engineers learn distributed systems for backend interviews, system design interviews, cloud-native applications, microservices, databases, messaging systems, caching, scalability, fault tolerance, high availability, real-world production systems. A common learning topic is, what are the most important distributed systems interview questions? This guide explains. Distributed systems basics: scalability, availability, reliability, latency, consistency, CAP theorem, replication, sharding, load balancing, caching, message queues, leader election, consensus, idempotency, retries, circuit breakers, distributed transactions, observability. Simple definition. A distributed system is a system made of multiple machines that communicate over a network to complete work. Example: user, load balancer, multiple backend services, database cluster, cache, message queue. Simple idea. One big system built from many smaller systems running on many machines. Why distributed systems matter. Modern applications are distributed because they need check, high traffic handling, fault tolerance, global users, faster response time, service isolation, independent deployments, scalability, resilience. Example: Netflix, Amazon, Uber, Google, banks, payment systems, social media apps, and cloud platforms all use distributed systems. Distributed system architecture. Typical cloud-native architecture. Frontend, API gateway, load balancer, microservices, cache, database, message queue, monitoring. Example: React app, Spring Boot API gateway, order service, payment service, inventory service, PostgreSQL plus Redis plus Kafka. Core distributed systems concepts. Concept meaning: scalability, ability to handle more load; availability, system remains usable; reliability, system works correctly over time; consistency, correct, latest data; latency, time taken to respond; fault tolerance, system survives failures; replication, copying data/services; sharding, splitting data across nodes; partitioning, dividing workloads/data; consensus, nodes agree on one value; idempotency, same request repeated safely. Question 1. What is a distributed system? Answer. A distributed system is a group of independent computers that communicate over a network and appear to users as one system. Example: multiple backend servers behind a load balancer. Real-world example: order service, payment service, inventory service, and notification service working together to process an order. Interview answer. A distributed system allows applications to scale, tolerate failures, and process work across multiple machines. But it also introduces network failures, consistency issues, latency, and coordination challenges. Question 2. Why are distributed systems hard? Distributed systems are hard because COC, network calls can fail; COC, latency is unpredictable; COC, machines can crash; COC, messages can be delayed; COC, messages can be duplicated; COC, data can become inconsistent; COCs can differ between machines; partial failures happen; debugging is harder. Important phrase. In distributed systems, failure is normal. Example: order service successfully creates an order, but payment service times out. Now the system must decide. Should we retry? Cancel the order? Mark it pending? Send compensation? Question 3. What is scalability? Scalability means the ability of a system to handle increasing load. Two main types. Type meaning vertical scaling, add more CPU RAM to one machine. Horizontal scaling, add more machines. Example: upgrade server from 4 CPUs, 16 GB RAM to 16 CPUs, 64 GB RAM. Benefits: simple, fewer architecture changes. Limitations: Hardware limit, expensive, single point of failure. Horizontal scaling. Example, run 10 backend servers instead of 1. Architecture. Load balancer down, server 1, server 2, server 3, server 4. Benefits. Check. Better scalability, better availability, better fault tolerance. Challenges. Distributed state, load balancing, data consistency, session management. Question 4. What is availability? Availability means the system is up and usable. Example, if users can access the app, it is available. High availability means system continues working even if some components fail. Example architecture. Load balancer, blank, service instance 1, service instance 2, service instance 3. If one instance fails, traffic goes to the remaining healthy instances. Question 5. What is reliability? Reliability means the system performs correctly over time. Availability asks, is the system up? Reliability asks, is the system working correctly? Example, payment API is available, but sometimes charges customers twice. That system is available but not reliable. Question 6. Availability versus reliability. Concept, meaning, example. Availability. System is accessible, API responds. Reliability. System behaves correctly. Payment processed once. Durability. Data is not lost. Order saved after crash. Interview answer. Availability means users can access the system. Reliability means the system produces correct results consistently. A system can be available but unreliable if it responds with wrong data. Question 7. What is latency? Latency means time taken to complete a request. Example, user clicks button, API request sent, server processes, response returns. Total time equals latency. Common latency sources. CUC, network delay. CUC, database query. Cache miss. CUC, service-to-service call. CUC, serialization. CUC, queue delay. CUC, slow external API. Question 8. Latency versus throughput. Concept, meaning. Latency, time for one request. Throughput, number of requests handled per second. Example, latency equals one order takes 200 milliseconds. Throughput equals system handles 5,000 orders per second. Interview answer. Latency measures speed for one request. Throughput measures total capacity. A system can have high throughput but still have high latency for some requests. Question 9. What is CAP theorem? CAP theorem says a distributed data system can strongly guarantee only two of these three at the same time: consistency, availability, and partition tolerance. Consistency, availability, partition tolerance. Letter meaning C, consistency A, availability P, partition tolerance. CAP theorem, simple explanation. Every read gets the latest write. User updates balance to $100. Every node immediately shows $100. Every request gets a response. Even during problems, the system responds. Partition tolerance. System continues despite network split. Node A cannot talk to node B, but both are still running. Question 10. Explain CAP with example. Imagine two database nodes. Database node A. Database node B. Network breaks between them. Now a user writes data to node A. Another user reads from node B. Choice. Should node B respond with possibly old data or reject the request until it syncs? If node B responds, availability is preserved. Consistency may be lost. If node B refuses, consistency is preserved. Availability is reduced. Interview answer. During a network partition, a system must choose between consistency and availability. Because network partitions can happen in distributed systems, partition tolerance is usually required. Question 11. What is strong consistency? Strong consistency means after a write completes, all future reads return the latest value. Example, balance updated from $50 to $100. Every read after update returns $100. Used in check banking, check payment systems, check inventory deduction, check account balances, check critical business transactions. Trade-off may increase latency or reduce availability. Question 12. What is eventual consistency? Eventual consistency means data may be temporarily inconsistent, but eventually all nodes become consistent. Example, profile photo updated. Some users see old photo for a few seconds. Eventually, everyone sees new photo. Used in social media feeds, analytics, search indexes, notifications, recommendation systems, replicated caches, interview answer. Eventual consistency improves availability and scalability, but users may temporarily see stale data. Question 13. Strong versus eventual consistency. Features strong consistency, eventual consistency. Latest data, immediate, eventually. Latency, higher, lower. Availability can be lower, higher. Complexity, higher, medium. Use case, banking, social feeds. Simple rule. Use strong consistency for money, inventory, and critical state. Use eventual consistency for feeds, analytics, notifications, and search. Question 14. What is replication? Replication means copying data or services across multiple machines. Example, primary database, replica database 1, replica database 2. Benefits: high availability, read scalability, disaster recovery, fault tolerance. Challenges: replication lag, consistency issues, conflict handling, failover complexity. Question 15. Primary replica replication. Architecture. Primary DB dot writes, replica DB1, replica DB2. Writes go to primary. Reads can go to replicas. Benefits: scale reads, backup failover, reduce primary load. Problem: replica lag. Example, user updates profile. Immediate read from replica may show old profile. Question 16. What is sharding? Sharding means splitting data across multiple databases or nodes. Example, user IDs 1 to 100,000 means shard 1. User IDs 100,001 to 200,000 means shard 2. User IDs 200,001 to 300,000 means shard 3. Benefits: handles large data, improves write scalability, reduces load per database. Challenges: cross-shard queries, cross-shard key, shard key choice, distributed transactions. Question 17. How do you choose a shard key? Good shard key should distribute data evenly, avoid hot partitions, match common query patterns, be stable, support scaling. Bad shard key. Country: if most users are from one country. Better shard key. User ID hash. For even distribution. Interview answer. A good shard key balances load and supports query patterns. A core shard key creates hotspots and uneven data distribution. Question 18. What is load balancing? Load balancing means distributing traffic across multiple servers. Architecture: client dash load balancer dash server 1, server 2, server 3. Benefits: check, better scalability, high availability, failover, better resource usage, common algorithms, round robin, least connections, weighted routing, IP hash, latency-based routing. Question 19. What is health check? Health check determines if a service instance is healthy. Example, get/actuator/health. If service is unhealthy, load balancer stops sending traffic to it. Types: check meaning Liveness. Is app alive? Readiness. Can app receive traffic? Startup. Has app started successfully? Question 20. What is caching? Caching means storing frequently used data in a faster location. Example: request product details. Check Redis cache. If found, return quickly. If not found, query database. Benefits: lower latency, reduced database load, better scalability, improved user experience. Common cache tools: check Redis, check Memcached, check CDN, check browser cache, check application memory cache. Question 21. Cache aside pattern. Cache aside flow. Application checks cache. Cache hit means return data. Cache miss means query database. Store result in cache, return data. Pseudocode. Product equals Redis get product ID. If product equals null, product equals database.find product ID. Redis set product ID product. Return product. Use for product details, user profile, configuration, category data. Question 22. Cache invalidation. Cache invalidation means removing or updating stale cache data. Example: product price changes in database. Cached product still has old price. Solutions: TTL expiration. Delete cache on update. Write through cache. Event-based invalidation. Versioned cache keys. Important phrase: cache invalidation is one of the hardest problems in distributed systems. Question 23. What is idempotency? Idempotency means doing the same operation multiple times has the same result as doing it once. Example: post/payments. If client retries due to timeout, payment should not be charged twice. Solution: use idempotency key. Example header: idempotency key ABC123. Backend stores ABC123 means payment result. If same key comes again, return same result. Do not charge again. Question 24. Why is idempotency important? Distributed systems have timeouts, retries, duplicate messages, network failures, partial failures. Without idempotency, duplicate payments, duplicate orders, duplicate emails, duplicate records. With idempotency, correct, safe retries, reliable APIs, better fault tolerance. Use idempotency for check payment APIs, check order creation, check booking systems, check message processing, check external API calls. Question 25. What is retry? Retry means trying a failed operation again. Example: payment service timeout. Retry after 1 second. Retry after 2 seconds. Retry after 4 seconds. Best practices: yes, retry only transient errors. Use exponential backoff. Add jitter. Set max retry limit. Make operations idempotent. Avoid ZAX, infinite retries. ZAX, retrying validation errors. ZAX, retrying storms. ZAX, retrying non-idempotent operations blindly. Question 26. What is exponential backoff? Exponential backoff means wait longer after each retry. Example: retry 1, wait 1 second. Retry 2, wait 2 seconds. Retry 3, wait 4 seconds. Retry 4, wait 8 seconds. Add jitter. Random small delay. Why? Prevents all clients from retrying at the exact same time. Question 27. What is circuit breaker? Circuit breaker prevents repeated calls to a failing service. States. State, meaning closed calls allowed, open calls blocked, half open, try limited test calls. Service fails repeatedly. Circuit opens, calls fail fast. After timeout, try again. If healthy, close circuit. Use for external APIs, payment services, Slow dependencies, overloaded systems. Question 28. Circuit breaker versus retry. Concept purpose. Retry, try again after failure. Circuit breaker, stop calling failing service. Simple rule. Retry helps with temporary failures. Circuit breaker protects system from repeated failures. Example. Payment provider is down. Retries can make it worse. Circuit breaker stops calls temporarily. Question 29. What is timeout? Timeout means stop waiting after a configured time. Example. Payment service call timeout equals 2 seconds. If no response in 2 seconds, fail request or fallback. Why important? Without timeout, threads get stuck. Resources are exhausted. Cascading failures happen. Best practice. Always set timeouts for network calls. Question 30. What is bulkhead pattern? Bulkhead isolates resources so one failure does not take down everything. Example. Payment calls use thread pool A. Email calls use thread pool B. Inventory calls use thread pool C. If payment service is slow, only payment thread pool is affected. Other services continue working. Used for thread pools, connection pools, service isolation, tenant isolation. Question 31. What is message queue? A message queue allows services to communicate asynchronously. Example. Order service sends event queue, Kafka, RabbitMQ, notification service. Benefits. Check. Decoupling, async processing, buffering, retry handling, better resilience. Common tools. Kafka, RabbitMQ, Amazon SQS, Google PubSub, Azure Service Bus. Question 32. Synchronous versus asynchronous communication type. Example. Pros, cons. Synchronous, REST call, simple immediate response, tight coupling. Asynchronous, Kafka event, decoupled, resilient, eventual consistency. Synchronous. Order service calls payment service and waits. Asynchronous. Order service publishes order created event. Payment service processes later. Question 33. What is event-driven architecture? Event-driven architecture means services communicate using events. Example. Order created. Payment service consumes inventory service, consumes notification service, consumes. Benefits. Decoupled services, scalable processing, async workflows, better resilience. Challenges. Eventual consistency, duplicate events, ordering issues, debugging complexity. Question 34. What is exactly once delivery? Exactly once delivery means each message is processed exactly one time. In real systems, this is hard. Most systems offer at least once delivery, meaning message may be delivered more than once. So, consumers must be idempotent. Interview answer. Exactly once is difficult in distributed systems. A practical approach is at least once delivery, plus idempotent consumers. Question 35. What is at least once delivery? At least once delivery means message will be delivered one or more times. Benefit. Message is unlikely to be lost. Problem. Message may be duplicated. Solution. Impotent consumer. Deduplication key. Processed message table. Transaction log. Example. Email notification event is received twice. Consumer should avoid sending duplicate email. Question 36. What is dead letter queue? Dead letter queue stores messages that cannot be processed successfully. Flow. Message processing fails. Retry several times. Still fails. Move to DLQ. Use DLQ for debugging bad messages, manual investigation, replay after fix, preventing queue blockage. Question 37. What is distributed transaction? Distributed transaction means a transaction that spans multiple services or databases. Example, order service creates order, payment service charges card, inventory service reserves stock. Problem. What if payment succeeds, but inventory fails? Distributed transactions are complex because each service owns its own data. Question 38. What is two-phase commit? Two-phase commit is a protocol for distributed transactions. Phases. 1. Prepare. 2. Commit. Flow. Coordinator asks all services, can you commit? If all say yes, commit. If any say no, rollback. Problems. No blocking. No coordinator failure. No reduced availability. Not ideal for many microservices. Question 39. What is saga pattern? Saga pattern manages distributed transactions using a sequence of local transactions. Example: create order, charge payment, reserve inventory, send confirmation. If a step fails, run compensation actions. Example: compensation. If inventory reservation fails, refund payment and cancel order. Question 40. Orchestration versus choreography. Saga orchestration. One central coordinator controls workflow. Order Saga orchestrator. Payment service. Inventory service. Notification service. Benefits: easier to understand. Centralized control. Easier monitoring. Drawback: coordinator can become complex. Choreography. Services react to events. Order created means payment service, payment completed. Means inventory service, inventory. Reserved means notification service. Benefits: check, decoupled. No central coordinator. Drawback: dash, harder to trace. Event flow can become complex. Question 41. What is consensus? Consensus means multiple nodes agree on a value. Used for leader election, distributed locks, cluster membership, replicated logs, configuration management. Examples of consensus algorithms: check, Raft, Paxos, Zab. Simple example: which node is leader? All nodes must agree. Question 42. What is leader election? Leader election means choosing one node as the leader. Example: node A, node B, node C. One becomes leader. Leader responsibilities: coordinate writes, schedule jobs, manage cluster decisions, assign partitions, coordinate replication. If leader fails, new leader is elected. Question 43. What is split brain? Split brain happens when a distributed cluster is split and multiple nodes think they are leaders. Example: network partition. Node A thinks it is leader. Node B also thinks it is leader. Problem: NICs, conflicting rights. NICs, inconsistent data. NICs, corruption risk. Prevention: quorum, consensus, fencing tokens, leader leases, majority voting. Question 44. What is quorum? Quorum means minimum number of nodes required to make a decision. Example: 5 nodes quorum equals 3. If 3 nodes agree, decision accepted. Why? Prevents split brain. Improves consistency. Question 45. What is distributed lock? Distributed lock ensures only one process across multiple machines performs a critical operation. Example: only one service instance should run daily billing job. Tools: C. Redis lock, C. Zookeeper, C. etcd, C. database lock. Warning: distributed locks are tricky. Use carefully with timeouts, ownership tokens, and failure handling. Question 46. What is clock skew? Clock skew means system clocks on different machines show different times. Example: server A, time 10:00, server B time 10:05. Problems: event ordering, token expiry, log analysis, distributed locks, timeout logic. Solution: NTP, logical clocks, vector clocks. Avoid relying only on wall clock ordering. Question 47. What is back pressure? Back pressure means slowing down producers when consumers cannot keep up. Example, producer sends 10,000 messages per second. Consumer handles 1,000 messages per second. Without back pressure. Queue grows, queue memory grows, system crashes. With back pressure. Producer slows down, queue remains controlled, system remains stable. Question 48. What is rate limiting? Rate limiting controls how many requests a client can make. Example, 100 requests per minute per user, used to protect against abuse, traffic spikes, brute force attacks, expensive API usage, noisy clients, algorithms, comma, token bucket, leaky bucket, fixed window, sliding window. Question 49. What is throttling? Throttling means intentionally slowing or limiting requests. Rate limiting usually rejects extra requests. Throttling may delay or reduce processing. Example, process only 100 requests per second from one tenant. Use for check multi-tenant systems, API fairness, cost control, overload protection. Question 50. What is graceful degradation? Graceful degradation means system continues with reduced functionality when something fails. Example, recommendation service is down. Homepage still loads without recommendations. Better than out. Entire homepage fails. Use fallback. Show popular products instead. Question 51. What is failover? Failover means switching to backup system when primary fails. Example, primary database fails. Replica promoted to primary. Application continues. Failover can be 6. Automatic, 6. Manual. Challenges. Data loss risk, DNS delay, replication lag, split brain. Question 52. What is disaster recovery? Disaster recovery means restoring service after major failure. Examples, region outage, database corruption, data center failure, ransomware, accidental deletion. Important metrics. Metric meaning RTO, recovery time objective, RPO, recovery point objective. Question 53. RTO versus RPO, recovery time objective. How long can system be down? Example, RTO equals 30 minutes, RPO, recovery point objective. How much data loss is acceptable? Example, RPO equals 5 minutes. Interview answer. RTO is acceptable downtime. RPO is acceptable data loss. Question 54. What is observability? Observability means understanding system behavior using telemetry. Main pillars. Check, logs, metrics, traces. Observability helps answer what happened, where did it happen, why did it happen, who was affected. Question 55. Logs versus metrics versus traces. Signal use. Logs, detailed event records. Metrics, numeric trends. Traces, request journey across services. Example, log, payment failed for order 123 metric. Payment failure rate equals 5%. Trace, request spent 2 seconds in payment service. Question 56. What is distributed tracing? Distributed tracing tracks a request across multiple services. Example, frontend, API gateway, order service, payment service, database. Trace shows each service call, latency per step, error location, request path. Useful for, debugging latency, microservice troubleshooting, incident analysis. Question 57. What is correlation ID? Correlation ID is a unique ID attached to a request across services. Example, X correlation ID ABC-123. Each service logs correlation ID ABC-123. Benefit. You can trace one request across many logs. Question 58. What is API gateway? API gateway is the entry point for client requests. Responsibilities. Check routing, check authentication, check rate limiting, check cores, check request transformation, check logging, check load balancing, check TLS termination. Architecture. Client, API gateway, microservices. Question 59. API gateway versus load balancer. Component purpose. Load balancer distributes traffic. API gateway routes and manages API concerns. Load balancer. Which server should handle request? API gateway. Which service should handle request? Is user authenticated? Should request be rate limited? Question 60. What is service discovery? Service discovery helps services find each other dynamically. Example. Order service needs payment service address. Instead of hard coding http://10.0.1.25, use payment service. Examples. Kubernetes Service DNS, Console, Eureka, etcd. Step-by-step interview preparation roadmap. Step 1. Learn basics. Learn. Distributed system definition, scalability, latency, availability, reliability. Goal. Explain distributed systems simply. Step 2. Learn data concepts. Learn. Check replication, sharding, consistency, eventual consistency, strong consistency, quorum. Goal. Explain how distributed databases work. Step 3. Learn communication. Learn. REST, gRPC, message queues, Kafka, RabbitMQ, sync versus async, event-driven architecture. Goal. Explain service communication trade-offs. Step 4. Learn resilience. Learn. Circuit breaker, backhead, fallback, graceful degradation. Goal. Explain how systems survive failures. Step 5. Learn transactions. Learn a terminal, distributed transactions, two-phase commit, saga pattern, orchestration, choreography, idempotency. Goal. Explain order, payment, inventory workflows. Step 6. Learn observability. Learn. Check logs, check metrics, check traces, correlation ID, check alerting, check dashboards. Goal. Explain how to debug production distributed systems. Top scenario-based interview questions. Scenario 1, payment timeout. Question. Order service calls payment service and times out. What should you do? Answer. Check. Set timeout. Retry only if safe. Use idempotency key. Mark order as pending. Avoid duplicate payment. Use circuit breaker. Reconcile later. Good answer. I would make payment requests idempotent using an idempotency key. If timeout happens, I would not blindly create another payment. I would retry with backoff or check payment status before retrying. Scenario 2. Duplicate Kafka message. Question. Kafka consumer receives the same order created event twice. How do you avoid duplicate processing? Answer. Make consumer idempotent. Use event ID. Maintain processed events table. Use unique constraints. Ignore already processed event. Example. Before processing event ID equals 123, check if event ID already processed. If yes, skip. Scenario 3. Database replica lag. Question. User updates profile but immediately sees old data. Why? Answer. Write went to primary. Read came from replica. Solutions. Read after write from primary. Session consistency. Delay read. Show optimistic UI. Reduce replication lag. Scenario 4. Service is slow. Question. One downstream service is slow and your API is hanging. What do you do? Answer. Check set timeout. Check use circuit breaker. Check use fallback. Check isolate thread pools. Monitor latency. Add caching if appropriate. Check degrade gracefully. Scenario 5. High traffic spike. Question. Traffic suddenly increases 10x. How do you handle it? Answer. horizontal scaling, load balancing, caching, CDN, async queues, rate limiting, auto-scaling, database scaling, back pressure. Scenario 6. Order workflow across services. Question: how do you design order creation involving payment and inventory? Answer: use saga pattern. Flow: create order as pending, process payment, reserve inventory, confirm order. Failure: if inventory fails, refund payment and cancel order. Distributed systems best practices. Design for failure: use timeouts for all remote calls. Use retries carefully. Make operations idempotent. Use circuit breakers. Use async messaging where useful. Avoid distributed transactions when possible. Use saga pattern for workflows. Monitor logs, metrics, and traces. Use correlation IDs. Plan for replica lag. Design for graceful degradation. Use caching carefully. Choose consistency level based on business need. Protect system with rate limiting. Test failure scenarios. Common beginner mistakes. 1. Assuming network calls always work. Bad. Service A calls service B and assumes success. Better. Handle timeout, failure, retry, fallback, and duplicate requests. 2. Retrying without idempotency. Bad. Retry payment request without idempotency key. Problem: customer may be charged twice. 3. Ignoring replica lag. Bad. Write to primary. Read from replica immediately. Expect latest data. Better. Use primary read for read after write critical paths. 4. Making everything strongly consistent. Bad. Force strong consistency for likes, views, analytics, notifications. Better. Use eventual consistency where business allows. 5. No observability. Bad. No logs, no metrics, no traces. Better. Use correlation ID, structured logs, metrics, and tracing. 6. Not setting timeouts. Bad. HTTP client waits forever. Better. Set connection timeout and read timeout. 30-day learning plan, week 1, basics. Learn. CAC. Scalability. Availability. Reliability. Latency. Throughput. CAP theorem. Consistency. Practice. Explain each concept with one real example. Week 2. Data and communication. Learn. Replication, sharding, caching, queues, sync versus async, event-driven architecture. Practice. Design product catalog and order system. Week 3. Resilience. Learn. Check. Timeout. Retry. Circuit breaker. Bulkhead. Rate limiting. Back pressure. Idempotency. Practice. Design payment API with safe retries. Week 4. Advanced systems. Learn. Saga pattern. Distributed transactions. Consensus. Leader election. Observability. Disaster recovery. Practice. Design distributed order processing system. Real-world project idea project. Distributed order processing system. Architecture. React frontend. Portal dot. API gateway. Order service. Kafka. Payment service. Inventory service. Notification service. PostgreSQL. Redis. Features. Create order. Process payment. Reserve inventory. Send notification. Retry failed payment. Idempotency key. Event-driven workflow. Dead letter queue. Distributed tracing. Circuit breaker. Redis cache. Service health checks. Concepts practiced. Saga. Microservices. Async messaging. Saga pattern. Eventual consistency. Idempotency. Observability. Resiliency. Final summary. Distributed systems are essential for modern backend, cloud-native, and system design interviews. Important concepts include scalability, availability, reliability, latency, CAP theorem, consistency, replication, sharding, caching, load balancing, message queues, event-driven architecture, idempotency, retries, circuit breakers, distributed transactions, saga pattern, consensus, leader election, observability. Key idea. Distributed systems are about building software that continues working correctly, even when machines, networks, services, and databases fail.